Okay, so we will continue with examples on the common source with degeneration, common gate, and source follower. So we'll take multiple examples and hopefully you will be clear about this concept. So the first thing, when you get any circuit, you need to identify which type it is. Is it a common source? Is it a common source with degeneration, common gate, or source follower? So in order to identify that, you need to look where is the input is being applied and where the output is taken from. So in this example, which we see here, as you can see, the input is applied at the gate of the transistor. The output is taken from the drain. And there is no resistor on the source side. This makes it just a normal common source. And the general equation for the gain of a common source is minus Gm times Rd in parallel with the R out. Now, what you are supposed to do, you just need to identify what is your Rd here, what is your load resistor, what is the resistor that you are seeing at the drain. If we look at the drain side, we can see from the V out, we have two connections here, one connection to M2 and the other connection to M3. You can see M2, we are connecting to the drain of M2, D2, and here we're connecting to the source of M3, S3. When I connect to the drain of a transistor, I see an R out. So here I will be seeing an R out 2 down. And when I connect to the source side of a transistor, we are going to see an 1 over GM3 in parallel with the R out 3. Okay, so my overall RD here, is basically the parallel combination of R out 2 in parallel with the 1 over GM3 in parallel with the R out 3. Those two transistors, their equivalent resistors, they appear in parallel with each other. And therefore, my overall gain minus GM with GM1. Why GM1? Because it's the transistor who's doing the amplification. The input is being applied on it. GM times RD, what is going to be RD? Again, it's R out 2 in parallel with the 1 over GM3 in parallel with the R out 3. And missed is in parallel with the R out 1. I missed this. There is another in parallel. R out of the main transistor, R out 1. Okay. So if you were asked about R out, so it will be 1 over GM3 in parallel with the R out 1, in parallel with the R out 2, in parallel with the R out 3. Means from V outside, if you look up, you find R out 1. If you look on this one, it's R out 2. And if we look here, it's 1 over GM3 in parallel with the R out 3. With respect to V out, they are all appear in parallel with each other. And that's what we are seeing here in the relation of R out. Now let's see this example again. Our first step is to identify the type of this amplifier. So our input is given on the gate of this transistor, and why is not there? And the output is taken. Yes, output is taken from the drain of this amplifier. And where is the source? The source is here. So this is a common source with degeneration. Why degeneration? Because you can see that the source is not connected to ground. There is something there, which is a diode connected transistor M3. So this is a diode connected transistor. Why diode connected? Again, because the gate and the drain, they are shorted with each other. And we discussed that this the transistor in this connection, it has an impedance that's equal to 1 over GM3 in parallel with the R out 3. Similar as if you were looking from the source side of the transistor. Now, what about our RD? Our RD, which is connected to the D here, is a transistor M2, and we are looking from the side drain of M2. This is source of 2 and this is the gate of 2. Since we are looking from the drain of M2, this makes we have an impedance, high impedance of R out 2. So now this is our RS and this is our RD. And we said typical relation of a common source with degeneration, it's minus RD over 1 over GM plus RS. Okay, so now what I'm going to do is just replacing the value of RS with RS in the general equation and the value of RD in this particular circuit with the value of the RD here. So it will be minus R out 2 over 1 over GM1. Again, GM1 because it is the transistor who's responsible for doing the amplification task, plus RS. RS here is 1 over GM3 in parallel with the R out 3. Okay. And this is what we just did here. Now let's see this example. Again, the first step, identify. So here I have two different circuits. This is the gate of transistor, this is the source, and this is the drain. Okay, so the input is applied at the gate of the transistor and output is taken from the drain. Source is it's not connected to any resistor. It's going to be grounded in the small signal model. This is just a common source. So the gain, the general gain is minus GM R out in parallel with the RD. Now, what is my RD here? RD is all the resistor that I am seeing here down at the drain of M2. It's not just an R out. We have to be careful because the source is not connected to ground. Here, it's, as we saw before, for the case of a degeneration of the transistor. So the RD here is going to be, the RD is going to be GM2 R out 2 times RS plus R out 2 plus RS. We discussed this when we found the output impedance in the case of degeneration of our transistor. Okay, so now therefore my gain will be minus GM1 times R out 1 in parallel with the GM2 R out 2 RS plus R out 2 plus RS. Okay, let's just divide our circuit, our screen into two halves. And what we are going to do now, so this is our gain. Now we will look at the other example, which is basically a common gate stage. Yeah, I should not say this. We should discover it with each other. So this is the source, this is the drain, and this is the gate. Since my input is applied at the drain side of the amplifier, what we are going to do is that we will figure out that this is going to be a common gate. Input is applied at the source and the output is taken from the drain. Now let's find the gate of the amplifier. Okay, so the general gain of a common gate is GM-RD, but we here have a source impedance, so not entirely Vn is applied at the source of the amplifier. So we need to, if we call this node X, and we have Vx here, so we have Vx is basically equal, I'll just remind you how we do it, 1 over GM over RS plus 1 over GM times Vn. And how from where we reach to this conclusion, if you remember, we replace the entire amplifier. Here we must assume that lambda equals to 0. We will have 1 over GM, our GM2, our input impedance of the amplifier. So we replace the entire amplifier with its input impedance, and we have the value of RS here, the resistor, and the source Vn. And we're trying to find Vx here. So Vx, we can find it from this voltage divider, and then V out over Vn will equal to V out over Vx times Vx over Vn. Therefore, V out over Vx is the gain GMRD, GM2. And yes, we need to replace our RD times V1 over GM2 over 1 over GM2 plus RS. Okay. Now, what is RD here? RD is the resistor that I am seeing looking up at the transistor M1, which is going to be the, since it is from the drain of M1, it's going to be out 1. Okay, so the entire gains, sorry for the mess up, GM2 are out 1 over GM2 over 1 over GM2 plus RS. So again, we did the voltage divider to find what exact portion of Vn arrived at the source of M2 that is going to be amplified with the gain of a GMRD. Okay. Okay, if we simplify this, and then we will basically arrive to this relation. I think there might be some issue in it. This should be R out 1 and not 2. I'll fix the slide. Okay, now let's take more example. So let's find the gain with respect to V out 1 over Vn, and then V out 2 over Vn. Okay, now V out 1, let's see, Vn is basically applied at the gate of transistor. V out is taken from the source of the transistor. And therefore, it's going to be a source follower here. This is a case of a source follower. And we discussed the general case of a source follower. The gain basically equals RL in parallel with the R out over 1 over GM plus RL over R out. I hope I did not make any mistake. Let me just verify this. Yes, I'm correct. Okay, so now we need to identify where is our RL. RL is basically the resistor that is connected at the source side. So here RL is basically formed through M2, and since it is from the side of the source of M2 as well, we will see 1 over GM2 in parallel with the R out 2. Okay, so our V out is going to be RL, which is 1 over GM2 in parallel with the R out 2 divided by 1 over GM1 plus this in parallel with the R out 1. This part is just the RL 1 over GM2 in parallel with the R out 2 in parallel with the R out 1. Now, what about V out 2 over Vn? V out 2 is taken from the drain of the amplifier, and the source is degenerated with this transistor M2. So the general gain of transistor with degeneration, common source with degeneration, if you remember, it's RD over 1 over GM plus RS. Okay, so now our RD is going to be what we are seeing at the drain side. We are seeing two transistors, M3 and M4. From M3, we are seeing it's connected to source side. Therefore, we will see 1 over GM3 in parallel with the R out 3. What about M4? M4 is connected from the drain side. So we will see an R out 4. And we discussed our RS is the same RS here. That is 1 over GM2 in parallel with the R out 2. Therefore, our gain will be, my RD is the parallel combination of all those. So it will be R out 4 in parallel with the 1 over GM3 in parallel with the R out 3 divided by 1 over GM1 plus RS is 1 over GM2 in parallel with the R out 2. So the trick here is to know what is your topology and know what is your RD and what is your RS. As simple as that. Okay, I think we're done here. Okay, now let's take this furthermore examples. So we need to find the gain. The input again is applied at the gate. Output is taken from the drain. Source is grounded. It's just a normal common source. So the gain is going to be minus GM RD in parallel with the R out. Now, what is our RD? Here, our RD is the parallel combination of those two transistors. On M3, we are seeing a diode connected to the transistor. Gate is shorted to drain, therefore its gain, its impedance, so it's 1 over GM3 in parallel with the R out 3. And on M2, we see drain side, so it's going to be R out 2. Therefore, the entire impedance, this is in parallel with the R out 2. So the gain of this circuit is minus GM1. RD is 1 over GM3 in parallel with the R out 3, in parallel with the R out 2, and in parallel with the R out 1. So all of this is just my RD, and this is the original R out 1. Okay. Now here we also want to find the gain, assuming that lambda equals to 0. So this is applied at the gate, taking out at the drain. Okay. So I think lambda of M2, what we are assuming that it's infinity. So we will see up just 1 over GM2, and down we will see 1 over GM3, if we are assuming those the lambdas for them are equal to 0. Okay, so since the source is not grounded, it's degenerated, the gain general will be minus RD over 1 over GM plus RS. So my RD is 1 over GM2. My RS is 1 over GM3. And my gain is going to be minus 1 over GM2 over 1 over GM1 plus 1 over GM3. Okay. And this is what we did correct. Now let's see this example here. Basically, we have this circuit where basically this is the input and this is at the gate. The output is taken from the drain. What about the source? Is degenerated or no? Yes, this is an ideal current source that typically have an infinite impedance. So let's look at this side, which is here. What we are seeing, we are seeing M2. M2, we are looking from the source of M2. So what do we see? We see 1 over GM2. So we will assume that this ignoring this all part can be replaced with a resistor that has a value of 1 over GM2. This simplifies our circuit. Vn, VDD, RD, and here 1 over GM2. This is M1. So it looks so clear now that it's a common source with degeneration. Again, the gain standard is minus RD over 1 over GM plus RS. Our RD remains as RD. The out is taken from here. What D is this? Let's fix it. However, our RS is being replaced with 1 over GM2, so the gain will be minus RD over 1 over GM1 plus 1 over GM2. 2, not 3. Okay. Now let's see this example. So we can see that the gate here, and this is the drain and this is the source. Input is being applied on the gate and the output is being taken from the drain side. The source is not grounded, it's degenerated. However, yes, still we didn't decide what's happening up. So this is a common source with degeneration. The standard gain equals minus RD over 1 over GM plus RS. My RS is a diode connected transistor M3, and I can see 1 over GM3 in parallel with R out 3. I think this should be clear by now about the impedance of a diode connected or impedance of a source or a drain. Now, what about up? What's happening up? Can we guess is it a diode connected? No, it's not as simple as that because there is the resistor RD here. And this is going to change things. So we need to be careful. Now, can I guess what it is? No. I need to do the small signal model for it in order to identify what impedance do I see up? What is my RD? So in order to do that, we need to apply a test source here and draw the small signal model. So it will be simplified to, no need to draw for the down part. We know what is happening. We just need to see what is the impedance seen up there. So there is an R out 2, and there is this voltage current source, sorry, GM2, V2, and this is my source is grounded, and here the drain, and I have between the drain and the gate an RD. So we are just looking at this point here between our drain and gate there is a resistor RD, and this is the gate point, and from this point we need to find what impedance do we see here. So this is V test and this current is I test. Okay, so the impedance that we will be seeing is V test divided by I test. Okay, so let's do this quickly. So we have, this is the V2. So V2 is equal to V test. Okay, and yes. So now we can find the equation. So let's make this loop here. So we have V test equals to I test multiplied with RD plus I test minus GM, GM2 times V test because V test is equal to V2, and all of this, so the current, the subtraction current, this is IT minus GM2 V test is the one flowing through R out 2. Okay, now let's take V test on one side. So V test multiplied with a GM2 times R out 2 plus 1 equals to I test with RD plus the remaining here R out 2. Okay, so V test over I test, which is equal the impedance seen up, our R, what should we call them, equivalent. Okay, it will equal to RD plus R out 2 divided by 1 plus GM2 R out 2. So this is the impedance that we see up there, that we should be replacing it with this value of the RD here. So the gain will equal to minus this impedance R equivalent divided by 1 over GM1 plus RS. What is our RS? 1 over GM3 in parallel with the R out 3. All these steps are summarized here. Okay, let's see this example. So the input is applied at the source of the transistor, here the source side, and the output is taken from the drain. This makes it a common gate, but you can see that there is an input impedance or a source resistance, and there is R1 too. So again, I need to find Vx, V out over Vn equals to Vx over Vn multiplied with V out over Vx. Okay, Vx over Vn again, we will have 1 over Gm. 1, the input impedance of the amplifier, we have R1, and we have Rs here, and we have Vn. Okay, so now, okay, so again, the voltage divider, Vx over Vn, this is Vx here, 1 over Gm1 in parallel with the R1 over 1 over Gm1 in parallel with the R1 plus Rs. And then if we do V out over Vn, it will be this part here, 1 over Gm1 in parallel with the R1 over 1 over Gm1 in parallel with the R1 plus Rs times GMRD. Now what is GMRD? The V out over Vx. GMR1 times RD. RD here is the resistor that we are seeing up, which is, since it's in the source of M2, it will be 1 over GM2. 1 over GM2 in parallel with R out 2. Yes, since we are considering it at infinity, we may ignore this part. Okay. It's fine. Now let's do this last example. So again, input is applied at the gate, at the source. Output is taken from drain. It's a common gate. Since the input directly applied at the source, we just have a gain of Gm RD. What is our RD here? The standard RD is the impedance that we are seeing up. So it is going to be this RD in plus, because they appear in series with what's happening here. We have a parallel combination of those two transistors. So it will be 1 over GM2 in parallel with R out 3, because for M3 we are looking from the drain side. So our gain will be GM1 plus RD, sorry, multiplied with RD plus 1 over GM2 in parallel with R out 2. Now lambda equal to 0, I'm at this moment assuming it for transistor M1, for M1. Okay. I'm also assuming it for M2, otherwise I can, sorry, this is R out 3. Okay, thank you.